Hi, everyone. Welcome. I'm Lerna Ekmekcioglu, Solutions Engineer at Clockwork Systems. And this is Rock Around the Clock, Synchronization. So if you're interested in how to improve performance with high precision time, stick around. Any application developers here? There's like one or two, okay. Three, I counted three. Any SREs? Lots of them. Okay. And have you seen this issue before? The app is slow, the claim is it's the network, fingers are pointed. But is it really the app or the network? I think as SREs, sometimes this becomes like a hot potato and we need to get to the bottom of it. So here I first have a demo of an e-commerce site that is going to get trampled over by a data workload because it is sharing the same network pipe. So I have about 10 plus microservices on top here. And this is what the e-commerce site is built upon. So this is a fully functional site. You can add items to your cart. You can place an order. You get some recommendations at the bottom. It's deployed on Kubernetes cluster. It's instrumented with OpenTelemetry API. So I'm going to kick off some load against the site just so I have some traffic. On top here, I'm going to first show you that I have tracing enabled. So each of these little dots, they're a full user journey from beginning to end. In this case, we started with the load generator. We went to the front end and so forth. And if you look at the requests themselves, on top I have request completion time graph. And below I have request stats. On the y-axis, I have in log scale 1 millisecond, 10 millisecond, and 100 millisecond for the request completion times. And right now, the max request completion time is at 140 milliseconds. All my tail latencies, like 99th and 98th percentiles, is at 130 millisecond. 95th is doing well as well. 90th is at 100 millisecond. 80th is 70 millisecond and below, and so forth. So the site is functioning fine right now. And on the system stats, I have system-wide delays in the microseconds range. I have 0 packets dropped right now, so no sender retransmissions. And on the throughput, I have about 180 megabits per second-ish. So this is why I call it a mice workload, because it has teeny tiny packets over the wire. So next, what I'm going to do is I'm going to kick off my data workload. This is my elephant workload. It's sharing the same network pipe as this mice workload, e-commerce site. So it's going to create some contention over the wire for it. The system-wide delays, they spike to about 1.8 milliseconds range at the same time as the sender retransmits, so number of packets dropped every second spiked up to about 28,000 packets dropped every second. The throughput right now is at around 145 gigabits per second on the inbound and the outbound. That's why this elephant workloads, chunky packets are trampling over the mice workload. So the request stats, max request completion time spiked up to around 5 seconds range. All the tail latencies also increased, 4.5 seconds for 99th and 98th. 95th is at 2.5 seconds. 90th is just spiked up to 2.2 seconds. Now, 80th percentile and below doesn't show the issue. They're still happily at 130 milliseconds and less, but we can see the increase in tail latencies caused by network contention just by starting this elephant workload. And I'm just going to refresh. And you can see those red and orange streaks, which are those increase in tail latencies for my mice workload. That's in about 5 seconds range or so. So we need accurate time, just so we can minimize those tail latencies and we can control congestion for performance. Compliance teams, they need accurate timeline of transactions so that they can prevent market abuse during times of flash crashes. And security team need accurate timestamps on requests so that they can prevent things like replay attacks. And it took us about 3,000 years to get the margin of error in measuring time down to a single minute. And that was with pendulum clocks. And before that, we used things like candle clocks and water clocks. And just like a pendulum swings at a precise frequency, we can make a quartz crystal vibrate at a precise frequency by cutting it to the right size and shape and applying electricity to it. And then it becomes an accurate oscillator that we use in our server clocks today. But the frequency of a quartz crystal degrades quadratically outside room temperature. It's not just the temperature that affects it, but vibrations from fan kicking in also affects it. So these quartz clocks that we have in our servers, they degrade. They drift up to 26 minutes in a year. We have to provide them true time from things like atomic clocks. They're much more precise, but more costly. So we may also use GPS clocks in our data centers. So we just have an antenna on the roof of the data center, and we pick up this very precise time signal from GPSs that have onboard atomic clocks. That naturally brings us to Bonnie and Clyde. Bonnie and Clyde, they were a famous couple during the time of Great Depression in the 1930s in the United States, and they robbed banks. And what is the number one thing that we need when we rob banks? Any bank robbers here? Okay. Well, we need to synchronize our clocks so that we can ensure a timely escape. So Bonnie and Clyde travel in time so they can use network time protocol. Clyde is the client and Bonnie is the server. At the end of this interaction with NTP request and response, Clyde has 4 timestamps, 2 of which is taken with his own clock, 2 of which are taken by Bonnie's clock, and Clyde is trying to figure out his offset from the servers just so he can correct his clock. And at time T4 is when Clyde is going to estimate that clock offset. What he needs to know is how long the response from Bonnie took to get to him over the wire. Then he can just take the difference of T4 and T3, which is Bonnie's response send time plus that response delay. Now in NTP, there's no way to estimate one-way delays, but we can estimate round-trip time with those 4 timestamps. It's nothing but that receive time for the response, T4, minus T1, which is the request send time on Clyde's side, the client side, minus the server processing time that didn't go over the wire, so we just subtract that from the total. So NTP has to make this assumption that request and response delays are equal and that response delay is round-trip time over 2, just so it can make this offset estimation. But in this estimate, there is a baked-in assumption that is affected by any path asymmetries in the forward and reverse directions between the client and the server that is going to contribute to clock synchronization errors. Once Clyde has this offset, cron-ED or something like that is going to slew the clock, which is just speeding up or slowing down the frequency of the clock, which is a best practice, because you're not only solving it for this point in time, for the offset, but also for the drift. So long as the offset is less than 125 milliseconds, or you can jump the clock to a point in the future or in the past, which is not ideal because your applications are going to see a time gap. Or if the offset is so large that most likely a hardware issue is at play, NTP won't do anything, so that's why we need to ensure to alert off of large clock offsets so a human can interfere, or our AI overlords can take over and fix the hardware issues. So during Great Depression, Bonnie and Clyde really didn't make much money from robbing banks because bank vaults were empty. But they do have a time machine, so they are going to use it to launch a hedge fund. Now, NTP cannot provide them the clock synchronization precision that they need because they need it at sub-microsecond level at this point. For that, they're going to use precision time protocol, which is an IEEE protocol. So it's a very electrical engineering protocol. And for PTP, for fine-grained accuracy, typically you'll need PTP-capable network cards and PTP-capable switches. So long as you're in charge of your own hardware and data centers and network and have some money, this is doable. Yesterday, Bonnie and Clyde told me they are expanding to the cloud, so I told them to meet me here in this room, and I noticed that all of you showed up. You technically weren't invited, but hey. So here's Huygens. It's another clock synchronization algorithm. It's one that was developed through Stanford Research. It's software-based, it's high precision, it measures one-way delays accurately. It relies on a few concepts that I'll walk through. First of all, it uses coded probes. So the idea is that you have a probe pair that is separated with a known distance in time that is sent by Clyde, received at Bonnie. So long as it's received with the same exact time gap at Bonnie, then it is a pure coded probe because it wasn't subject to any network delays or jitter in the network. Also, we not only send each other probes, but we can send probes to other neighbors. In this case, basically in Huygens, you're forming a probe mesh. You can talk to, say, 5 other nodes as well. And because temperature is a physical property and it doesn't fluctuate wildly over 2-second intervals, so every 2 seconds, the nodes are going to filter out the probe data that they have from their neighbors, from the mesh. For the pure coded probes, those are the probes that didn't suffer from network delays. And they're going to estimate at a high precision using a machine learning classifier for the offset and the drift. Now in NTP, you are doing pairwise synchronization. That's prone to errors due to path asymmetry. In Huygens, it leverages the idea that clock synchronization is transitive. So if you go around the subloops in the graph and you add up the offset around this loop, then if all clocks are synchronized, then it should add up to 0. So what Huygens does in this case is it's going to go around these subloops and it's going to minimize those errors that are due to path asymmetry. It's kind of similar to an idea of triangulation, for your location, for example. But it's not just doing it for 3 nodes, but more. It's also measuring one-way delays because once clocks are synchronized, then you have these probes. So you have a lot of probe data forward and back. So you can measure those one-way delays at a high precision. Which brings us to the problem at hand. So the transport protocols today, this is how they work. It's Clyde with a giant hose flooding Bunny until some intermediate buffer at a switch overflows, at which point Clyde is going to be retransmitting and timing out these packets, which then induces these tail latencies, which is what we saw in the demo. So this is another Stanford Research paper that is on congestion control. It detects congestion early and then it controls it. So basically, the idea is that you first have the sender and receiver clocks synchronized at a high degree of precision, so you know one-way delays accurately. And if those one-way delays go beyond a congestion indicating threshold, such as a minimum one-way delay plus some headroom, at that point, Bonnie is going to tell Clyde to pause for just a few microseconds. And that is enough for the intermediate buffer to drain, so we never have these retransmits and timeouts. And we can extend this, like optimize this, one step further. Why do we even use the buffers in the middle to begin with? They're unreliable. They introduce variability to the latencies that we have. So the idea is to keep a bandwidth headroom. You give up just a little bit of the bandwidth, very tiny. And you do that by using a counter at the receiver's end for the sender. So Bonnie has basically set a counter. She's counting the bytes coming in and out, and at 3.8 gigabits per second for Clyde to send her data. And if Clyde hits that, then Bonnie is going to tell Clyde to pause for just a few microseconds, and the buffer is going to drain a little. So this way, she's optimizing the good use of the throughput. So she never even gets to those buffers in the middle. She can extend this one step further. Because she decided that Clyde wasn't the best partner to start up these ventures to begin with. So she is going to set a higher allocation of the bandwidth for the Banshee. She gets 2.3 gigabits per second. So the zombie gets 1 gigabits per second. Clyde gets 0.5 gigabits per second until he gets his act together. So in this way, the receiver is slicing the bandwidth according to her own priorities based on the importance of the sender to her. So if it is the network, then we do have a choice. If we know the clock offsets and drifts at a high precision, and if we know the one-way delays, then we can detect and control upcoming congestion at a high precision. That's what these two papers are telling us about. And that's what my talk was about. Thank you.